Hey, what's up guys? So, this should be fun. I'd like to introduce you guys to Rob. So this is like Radenso's genius engineer. Would you like to introduce yourself and tell everybody a little about your background, experience?
Sure, my name is Rob Taylor. I'm part of John's engineering team over at Radenso. I come from a DoD contract engineering background, big DSP enthusiast. I've been doing engineering stuff since I was a kid, mostly for hobby and more recently for work. So definitely an enthusiast for DSP, receiver design, electronics, and found a really great group of people to apply that with, and we're having a lot of fun doing it.
Yeah, so I figure in this video, like, my favorite part of SEMA so far has just been talking to you and like learning and asking questions.
I'm flattered.
Hearing what you have to say. Like, I've been having a ball.
I'm glad to hear it. Yeah, it's been a lot of fun finding people who are really interested in this stuff and sharing that enthusiasm and kind of sharing this design philosophy with the people that come to the booth. It's just been a blast. So, yeah. So
I figure for this video, we can talk a little bit about Theia, which
Absolutely.
is the name of Radenso's new radar detector. We can talk about the AI, and I'd love to just let's just geek out and chat RF.
I can definitely do that.
Yeah. So I guess starting off, I've got a list of questions. I know things we were talking about. So I guess with Radenso's new radar detector you're working on, what different things are you able to see? Like, what characteristics of a radar signal are you able to tell?
So for signals, regardless of the radar or if they're BSM, which I guess is a subset of radar, or anything that's an RF signal, the things that we're looking at with this detector are the basic components of sinusoidal energy, right? So we're looking at phase, amplitude, and frequency, and the way those three components change as a function of time. And a radar signal is just like any other signal, with the exception that the majority of them are not intended to have modulation on them. But everything has modulation whether you like it or not, and that's kind of what we've been leveraging.
So like, what kind of things, when you see that there's modulation, what does that help you do?
Well, it's really great because when we take basically the fingerprint of a signal, what we're looking at is when you see a signal that looks almost indistinguishable from another signal, and which that's kind of how a CW radar looks. It's meant to just be pulsed energy, and if it was ideal, it would occupy no bandwidth. It would be perfect in amplitude, be very stable, it would have no phase noise.
So it would look like a spike, essentially.
It would just look like a spike in the spectrum, but that's not how things work realistically. Due to manufacturing constraints, engineering budget constraints, size, weight, and power constraints, every signal that comes out of a gun or a TV station or a Wi-Fi router, they all have modulation characteristics that are evident. You can see these carriers from the CW guns. We've seen kind of that swoosh of the instant on, right? That's a transient where the circuits are becoming energized and heating inside of the gun when you pull the trigger. But when a gun is already triggered, instant on aside, you see things like frequency stability. When that gun starts to heat, you start seeing that carrier slowly drift up or down in frequency. You see phase noise from the synthesizer design where there's modulation at the base of the carrier right near the noise floor. You see amplitude stability where the gun is showing drift in amplitude as a function of time. And sometimes these characteristics are so deterministic that you can use them to fingerprint a transmitter and identify it. And that's exactly what we're doing with the AI here.
And so those are the kind of things you're looking for to differentiate and classify signals.
Absolutely, and they look almost minuscule when you look at them at a very wide bandwidth, but when you filter them and do the DSP that we're doing, these things that are very low amplitude relative to the carrier become incredibly distinct when you look at them side by side.
So if you have like multiple copies of the same gun, are you able to tell this is all the same gun?
Absolutely so, and that was one of the coolest things to actually see, is to train on a Falcon and to make sure that we weren't overfitting to that serial number Falcon, but we were training to that class of gun. And the way that's possible, that all these Falcons, for example, right, have the same oscillator and the same synthesizer and the same feed horn and the same power supplies, and that's what we're training on. So we have to make sure that we don't overfit to a very specific emitter, but to the whole series of one emitter. And so we've very successfully trained on one gun in a few different configurations and then successfully inferenced on a whole range of other guns that we had in the shop.
What kind of differences do you see from gun to gun?
Actually, you see very little, unless a gun's been severely damaged from being dropped on the floor or dragged around the office, which never happens, in which case they are bizarrely out of tune. But even then, it's really interesting because we had, for example, I can't remember which gun it was, but we had trained on one, inferenced on a couple others, and one of them was so far to, I think it was 100 or 150 megahertz out of tune, and the signal characteristics were way distinct, but we still successfully inferenced on it. Not with the same certainty, but we were blown away that even with a damaged unit, we were seeing successful inference.
So this is the thing, we talk about like out-of-tune guns, and then maybe the radar detector can't detect it because it drifts off frequency and stuff.
And that's the thing, when people say, oh, it's really easy if you look for any gun at 24.125 gigahertz, but I think that's one of the things that's really hard to conceptualize, that the AI has no concept of frequency. everything in this quadrature sampling is based at 0 hertz with bandwidth extending in a positive and negative direction. It has no idea where that frequency is centered at 24, 35, 10 gigahertz. It just says, here's a signal. And that's what makes it really important is that the frequency of the gun when it's triggered does not have to do with the successful inferencing routine. Right? So we kind of divorce those two domains.
When you say quadrature, what does that mean?
Quadrature means that we are sampling the signal, and if there are DSP theorists or engineers out there, they're probably going to kill me for oversimplifying this, but when we sample in quadrature, it means that we're sampling the signal from two different perspectives, in phase and out of phase. So instead of having a series of samples representing a sine wave, for example, we have 2 data points for every sample, one showing the in-phase and quadrature component, and that lets us retain, it's called a vector data set. We get to see basically the signal from 2 perspectives at any given time, and at the risk of infuriating theorists, it kind of lets us do a lot more analysis on that signal and leverage a lot of techniques that aren't possible with a single data point or a scalar data set. And that's pretty conventional in most of the designs we see.
Is this related to, I know like they're calling it the phase view?
Right, phase view is kind of, it's more of a concept than anything, and what the whole point of this is that we tried to future-proof this technology in such a way that there are so many different algorithms that we can embrace as we grow this product and start encountering new threats, that including the ability to have this instantaneous bandwidth and this quadrature data set lets us not only solve problems now by recovering phase information and using that to help correlate when we do some of these operations, but it really future-proofs the design and stops us from over-constraining into just one-dimensional data.
So when you're talking about future-proofing, like what are some additional things you'd be able to do, or what do you hope?
Well, encountering, say this, when this product hits the market, there might be new emitters, new BSMs,
Sure.
new interferers, new door openers, any range of potential concerns that we have to then bring into our problem space, solve, and make sure we don't false alert to, or new threats from police guns or whatever it might be, speed signs, red light detectors, mobile units, things that we need to bring into our catalog of active threats. Future-proofing is having a design where the bottleneck or the constraints on what we can solve are so far outside of what we encounter now that gives us a lot of room to grow without having to re-engineer the product, and where we can upgrade things with a lot of modularity. And that's definitely one part of that. Having the ability to bring in low phase noise, high dynamic range, quadrature data really secures our ability to address threats as they arise, or to fix problems on release that we might not have encountered in the lab.
So when you talk about high dynamic range, what does that allow you to do?
So the dynamic range of the receiver is the range at which you can capture signals of various different amplitudes. And again, this is an oversimplification.
Well, like maybe that we get super loud audio, and our audio starts to clip here, or something that's too loud, too soft.
It's a really great analogy, really. If these guys next door are blasting drum and bass, right, and we can still hear each other very, very cleanly when we whisper from this far away, we have an environment with very high dynamic range.
Okay.
If we had to sit here and scream at one another to overcome that, it basically means that we can see very, very weak signals in the presence of very, very large signals, which is really important, because if you're behind something with a BSM in traffic and your radar detector is aiming right into the BSMs on the rear of that vehicle, but there's a police unit 2 miles down the road firing a KA-band gun, you want to be able to see that very low amplitude signal, even in the presence of this very high amplitude broadcast directly in front of you. And that's really what the dynamic range helps us leverage.
I remember we were talking about this a little earlier, and you were mentioning how like some may raise the noise floor because of the BSM, where you're able to maintain a large dynamic range?
Right, and basically that's a little bit harder to explain. Maybe we could do better with some graphic representation of that. I can maybe show you what dynamic range looks like and why it matters so much. We have some recordings of BSMs in the presence of a police gun fired in the same band, and you can see that we have these very, very strong signals and a very weak police gun kind of superposition in there with that data. And the dynamic range allows us to successfully inference on that. So it's really nice. It lets us have a lot of sensitivity, but express different signals of wildly different values in the same spectrum.
Somebody in the forum, I guess speaking of BSMs, they were asking, what if you take a police radar gun, or I guess if the cops are trying to defeat this technique, and they're like, well, let me take a BSM signal as my transmitter and use that to try and issue tickets to defeat this technique.
Well, first of all, it'd be really, really impressive if they had a radar gun that could fire at 200 megahertz bandwidth signal. It wouldn't be something we've seen so far, but it's really cool because this is a really great question. This is what's so important. One of the things that is a little bit conceptually challenging but super important about the product is that we're not training on this signal, right? We're not training on the way this thing sweeps up and down and does this, the different things that you see in the BSM signal. We are training on the characteristics of the platform that transmit it.
Okay.
So a BSM in a Cadillac, that transmitter in the back of the vehicle is the platform. If a police gun was firing, that police gun is the platform. If a police gun was firing a BSM signal, it would look like a police gun playing back a BSM signal. What we're training on are the electronics in the transmitter, not the signal itself.
So what characteristics of the electronics in the transmitters can you see?
Kind of the same thing we're talking about at looking at different serial number guns in the same family. You'd be seeing the phase noise added to by the oscillator configuration, the synthesizer. You'd be seeing the instabilities and frequency drift. You'd be seeing the transients when the playback started. All these different characteristics kind of get folded into that and kind of superimposed on the BSM waveform they might be playing back.
What about even like the power source that's powering the radar gun?
And that's another thing, and that's really a huge thing. That's the majority of what you see when you see that power on transient, right? You start seeing capacitors charging and all these other things taking place, and synthesizers heating, things with really high temperature coefficients that are drifting as a function of time. That's really interesting, because if you have a really weak power source or very noisy power source, we can see the difference in some of these door openers if we power them with two different power supplies.
Really?
Right, and so it's really interesting because there's a lot of potential there to say this is more of a concern. This signal that we're identifying is valid because it's coming off of a very poorly regulated cigarette lighter run by an alternator, right? So these are things that are absolutely a possibility.
So like differentiating something powered by a cigarette lighter versus a battery, a solar panel, is there capacity to differentiate that?
I think there absolutely is, and that a lot of that rests on the manufacturer of those devices, how much attention to detail they put into those part selections, and do they care what those first few microseconds of a trigger pull looks like, or do they care about this thing operating in the field for 20 years, right? We care about one way more than they do, right? And so it's really interesting how their design philosophy interacts with ours, and the things they care about might give us a huge advantage. So the answer is, in a lot of cases, it's absolutely the case, right? So,
man, that's interesting.
Yeah.
So I guess maybe also the environment, like when a radar signal is transmitting.
And that's something that's a huge concern too, right? Because if we're looking at these very small differences in phase and frequency shift, if you're following something like a semi-truck in traffic and it's basically this gigantic reflector in front of you, if a signal is hitting your horn and at the same time reflecting off of this truck some meters away and then also impinging on the horn, it's going to be coming in at a slightly different angle with a slightly different delay, and those two signals interact with each other. It's called multipath interference.
Yeah.
Our ability to successfully inference a multipath was something that was super nerve-wracking when we were trying to encounter it for the first time, but we're really successful in doing that, in that we can bounce signals off of moving vehicles and still inference on them even when we're stationary. And that's something that's insanely important to us, because especially in really dense high traffic environments, you're going to have signals, not just the incident signal hitting your horn, but those bouncing off the asphalt before it gets to your horn, bouncing off adjacent cars, basically all these different smaller amplitude copies of the same signal all arriving at different times. We have to basically sum those into one signal and see if we can inference on them.
The most that I've seen with this happening is like, we call them bouncy arrows, because the signal reflects coming behind you off the semi in front and then from the front. So a signal behind you looks stronger from the front.
Right. And I think that's another thing that's pretty important. Having this phase information, we can actually kind of look at the phase information carried with these samples to make sure that we're kind of correlating the correct data set. There's a lot of things you can do algorithm-wise to reduce multipath interference, to have adaptive equalization. These are all things that we can leverage with this kind of complex data set that we're bringing into the
What would be some of the benefits of, like, once you do that, what would be some of the benefits of doing that?
Well, what's really great is that we don't necessarily have to calibrate the entire frequency range of this entirely huge gigahertz wide range of frequencies. We can have channel selective filters, and we can have channel selective equalizers for kind of normalizing the signals that we're seeing. If we start seeing, if we need to do some sort of frequency correction to help us add contrast to one of these pictures that we send array, we can do that with some of these DSP algorithms. There's just, the answer is kind of a strange answer when we say we can do just about anything, and because I know it almost sounds a little bit soft and like salesmanship, but it's true. I mean, if we can express something we wish to do to that data set mathematically, the hard part is basically doing that, realizing it's almost trivial at that point.
So I guess maybe, like, to give a concrete example, you say maybe boosting the contrast of a signal.
Right.
If you were to do that, then what would that allow you to do?
Well, when we say boosting the contrast, I think we're making a lot of analogies here to like image processing, which we kind of talked about the other day.
Yeah.
When you boost the contrast, what we're trying to do is basically try to bring out the features that Ray is inferencing on. And to do that, we do things like polyphase filters, we do things like automatic gain control. We start running kind of what the DSP is doing is taking this raw data set from this very noisy environment and cleaning it up and proportioning it and adding contrast, adjusting brightness if you want to stay with that analogy, so that we send Ray a very consistent data set to make these inferencing decisions based off of.
Yeah. Do you see like maybe, I know there's like reflections, maybe hills and terrain. How does that affect your signal that you see?
Same thing. There's a lot of theory in here that I'm going to try not to use the words I want to use because I'm really
well, no,
excited
go for it. I'm like, no, I want to get more into this.
Well, there's a lot of things like when you start having difference between near and far field radiation effects, when you have impairments in your first Fresnel zone, there's all these different things, right, that terrain impact. But mostly is this frequency selective fading, which is, you know, when you have multipath coming in, when you have a reflected signal coming at a slightly different time than an incident signal, and if it comes in at the wrong phase, they'll actually cancel each other out and start dropping amplitude. You see a lot of that, but only at specific frequencies. So, I mean, there's so many variables for us to test, and we're just now starting to collect all that data, but it's everything that we can simulate within reason so far has been super promising.
So when you were talking about like phase change stuff, it kind of made me wonder about like different polarizations of the signal.
Right.
Circular versus linear and all that.
Right, and that's kind of important too, because when a signal is bouncing off this really complex environment, having all these different interactions, right? It doesn't matter if, you know, a lot of times I don't think a cop is sitting there with a laser level making sure it's horizontally polarized, right, or whatever it might be.
Yeah.
So when we train, we try to build this training manifold. Instead of just taking a gun and saying, okay, train on that, we're rotating the gun, we're firing it through, you know, we're bouncing the gun off different things, we're putting backscatter in there to try to add multipath. What we try to do to build up tolerance to stuff like polarization mismatch, which is a big problem.
And there's some radar guns that do that intentionally to try and defeat radar detectors.
You bet, you bet. What we try to do is collect every aspect we can of a gun, forward, backwards, reflected, incident, firing it through maybe like a box fan to try to put a bunch of like, yeah, I'm serious, like we do everything we can to try to add as diverse as a training set as possible. And the difference we see in inference quality when we really do that is astronomical.
Really?
Yeah, it's night and day.
Does that make your inferencing more accurate? Or?
Absolutely. So one of the things we were saying was that if you took a gun and you taped it to a table and you fired the trigger, it might look perfect, but when someone's holding it, one of the things we'd see when we were really doing this filtering and looking at these signals in very high fidelity is that when John would fire a gun at me, I could see his heartbeat and stuff like that by the way the gun was oscillating. I could see his hand twitching a little bit when he'd hold the gun. And so there's such a thing as too much information, right? And so these are things that we do. So now we have somebody come and grab the gun and their hand shaking them when they pull the trigger, right, and stuff like that. We integrate all that into the training set as well. So we really have as much diversity as we can possibly capture.
Like this is nuts, because normally from a radar signal you see what? Frequency, strength.
I mean, most of the time
Not
you say,
a lot.
I'm going to look at about this much spectrum, I'm going to look at it for some amount of time. Over that some amount of time, I'm going to take the average of how much energy was in this window I looked at and say, yeah, there's maybe a signal there, right?
Yep.
This is basically taking some amount of spectrum, throwing it in a box and weighing it. And we're just doing so much more than that.
So much more.
Right.
What about like, I know with yours you're using like a traditional horn antenna.
Sure.
I know you were also talking like off camera about different phased array setups.
Sure. That's another thing that when we have phase information, it lets you do this kind of processing that is huge amounts of utility. And now I'm going to say this just from the perspective of a quadrature receiver generally. When you have this kind of phase information, you can start building beamforming systems, right? You can
before I guess we get into that, we should talk about what is a phased array antenna.
Oh, yeah, sure. I guess that might make some sense.
Yeah, so this is totally different than what's being done here. It's just maybe getting into a little...
Right, it's just kind of geeking out a little bit, I guess.
Yeah.
But when you have phase information in your data set, it lets you take an array of antennas, basically 3 or 4 antennas or feed horns, and you can put these in a line. It's called a linear array, right? And you can with no moving parts, you can take these 3 antennas, and by changing the angle that you're collecting data on these guys or sending data, you can actually steer an invisible beam of where you want to point this thing. So you can almost, with no moving parts, point a feed horn very, very swiftly.
So it's kind of like rotating a traditional antenna, except you're steering electronically with no moving parts.
And that being the case, since it's just phase that you're using for that steering vector, you can steer this beam many thousands of times a second just by manipulating that data set. And what's kind of cool about that too is that if somebody's intentionally interfering with you, you can draw a null in that beam where you don't want to receive stuff, and you can steer that as well, right?
So I know that's kind of getting beyond the scope of this stuff,
but it's fun to talk about.
Maybe one of the nice things about this is like you've designed the whole system to be modular, so somebody could throw on a different antenna. They could, like you've been maybe discussing the idea of making it open source, and they could change something if they want. Like, what are your thoughts of other people participating that way?
This is something that we talked about, I think, a couple of days ago when we were just kind of spitballing this stuff.
Sure, yeah.
I totally acknowledge I'm not the best DSP engineer you're going to encounter. There are so many brilliant people that it would be irresponsible to say, all right, this product gets to work up to my competency, and that's where it stops, right? When you let these people who are insanely genius at this stuff come in and contribute, you get to let this community help build a product that they then get to enjoy more. And I think that's fundamental. Alongside that, everything I know about DSP has come from these people who shared their knowledge. A lot of the software that I've used to learn DSP has come from open source projects of these insanely generous people who have spent so much time doing this. It's almost giving back to the people who are funding us to do this. And when you share with people, everybody gets to enjoy it more. We could put a lot of energy into saying, okay, we got to protect this IP. The IP is the baby. The product experience is the rock star, right? Not the IP.
Well, it's funny because like this is actually super rare to have somebody sit down and be like, let's talk about how this stuff works, what's possible.
Right.
How does it work? What's it doing?
Yeah, and that's the thing is that I don't want to obfuscate that. I think that if you really use your diligence in design and you do something you're proud of, you have a lot less to hide. And if there's critiquing and there's criticism with any product, it doesn't matter
Always,
if it's, no matter how good we do, there's going to be people who are not happy with something, but having the ability to expose that to the community and say, hey, you are proposing something that makes a lot of sense. I wish I would have thought about that. I'm embarrassed. Let's roll it in and see if we like it. Let's put it in a development branch and release it to beta testers. Do they like it? Let's do some regression testing. Does it break anything else? Okay, it's part of it. Now, thanks for your contribution. We appreciate you, right?
So if somebody comes up with an idea, let's say that maybe it's a design choice or a design flaw or like improvements, what would your take on that be?
I would be incredibly grateful because there's one of me and there's however many thousands of users.
Yeah.
There's only so many corner conditions I can encounter. There's only so many situations, right? And so the more exposure we get, I totally anticipate having people say, hey, this isn't working right when this happens or when I'm doing this or in this
we see that all the
corner
time.
condition. Sure.
Yeah.
That stuff we could never simulate, but stuff that if we show people how this works, they can not only say, hey, I need this fixed, but they can say, and here's might be a good place to fix it. Here's my proposed fix. Here's a whole different way of doing this that gives you, this huge advantage you might not have thought of. And I don't know, I think the collaboration and being on this enthusiast to enthusiast platform makes me super excited.
So like when you're actually developing, what is a typical day for you like maybe in the lab? Like what's your experience like developing this?
It's about 16 hours of caffeine, yelling math at John across the top of his whiteboard, pacing back and forth, and having fun actually. So what our workflow might look like is we're doing some training on a gun and we're seeing maybe the training set wasn't very good. Maybe it said, oh, we only got 85% accuracy on this. What we do is then take some of those samples that we tried to train on and say, okay, what did this look, this one is actually getting this wrong. We're getting whatever this falcon confused with a talon. That should never happen. What's the difference here? And then kind of just doing a little bit of statistic analysis and saying, oh, listen, if we do this, let's see if we might retrain the same data 4 or 5 times in a day and see how we like it. And then start saying, oh man, we never thought of doing this, but when we do this, all these classes differentiate by another 10%, right? So that's kind of what our day looks like. It's just experimenting and yelling linear algebra at one another. So.
Do you have an idea of like what the detector is going to look like at the end of the day, or do you keep adding new features and ideas? Or?
Well, that's a really good question. I think that we know what the horn's going to look like because those dimensions are design critical, right? The dimensions of the horn and the way that the internals are built are a part of the critical design. But the data converter, the gain stage, a lot of the stuff that we can do after that are super modular. So the thing that's going to be, I think, one of the determining factors is the size of that horn. But a lot of the other stuff, we really have a lot of latitude there. And I think that the data we're collecting now, especially now that we have this prototype we can play with, is going to let us constrain the design and say, what's the point of diminishing returns? What was a bottleneck and what needs to be enhanced or decreased? And that's really going to start constraining itself as we do more experimentation.
Yeah.
Yeah.
Cool. What's been your favorite part of the experience so far?
Just the attitudes. The people that we're encountering it's unlike any other engineering team I've been a part of. All these people are enthusiastic and absolutely willing to experiment and embrace new technology, and I think that the culture here is basically its own thing. I've never really encountered this before, and so the personalities and the enthusiasm and the work ethic is just astronomical, and the fact that we're like these nerdy enthusiasts doing this for a bunch of enthusiasts, it really makes it feel more rewarding because I feel like we're kind of like taking care of our own, and it's just, I think that's the most satisfying thing is that we're not building a product for some 3-letter acronym agency that's gonna, that prints money. We're building for consumers that don't want to open their wallet for a piece of junk.
Like, they want good stuff.
Right, and
yeah.
I think that another thing that makes it fun is that a lot of the people that we're designing this for have been basically told, this is how good you get to have a product. And if you ask me to do something, I might not do it. And it's just such a weird market, so.
It's been a weird thing. Like, we've had fundamental limitations that I just assumed that was the case, and you're coming in like, nope, you can filter BSMs so easily.
Well,
like,
I think that
what?
There's a sense of the industry being at this neutral buoyancy point, right? Where it almost seems like this gentleman's agreement. We don't have to do better, everybody's buying it now, right? And I felt really good being part of a team that's kind of upsetting that model, so.
It's interesting because there's so many things here that are like, you're just able to do it so easily, and I didn't even know it was possible.
Well, that's the thing. I mean, it's just, they're not new techniques. I mean, every cell phone transmitter, every cable modem, every router, all these things are using these technologies, Quadrature, this IQ stuff, right? But this is just this little microcosm that hasn't been exposed to this technology. It's really not that revolutionary in most industries. But
I guess to us, it seems completely
right,
mind-blowing.
But to people who are so used to being constrained to this, very classical way of doing business, I can totally understand why it would look that way.
Yeah.
Right.
Well, thanks for coming in and like shaking stuff up for us, and
it's my pleasure, really.
Bringing us to the 21st century, apparently.
I'm having a blast. I can't wait. I've had a great time hanging out with you and talking shop, and I'd really like to do some more visual stuff. I'd like to engage with the community.
That would be good. I know we were talking about this kind of stuff before, and a big part of understanding and appreciating this is like when you can see it visually, you're like, oh, that's so cool.
Yeah, I know. Well, it's like when you can touch and see and feel math happening, it's way less abstract, right? You can see when you're changing a filter, you see the spectrum change, right? It's a lot easier to see what that is doing when there's not like a bunch of like weird curly W's and lowercase e's all, you know what I'm saying? Like you can kind of extract the math from the practical application, so.
Or even like sitting here talking about stuff. I know it'd be a lot easier for people if we had the visuals. I know you've been working on it in the past couple of days. And
yeah, it's just been it's been crazy. We've had so many people come through here that I've had to kind of pull aside and talk to.
It's been tough to like, so maybe that was something we could do in the future is actually show you more of this stuff and go into more detail.
It'd be a pleasure. I really like sharing this, so it's something I'd like to do more of.
And I love hearing you talk. It's a blast, so thank you.
Absolutely.
Cool, appreciate it.
Yep. Thanks.